It's time for some simulation, some scripting. We know how to evaluate the daily energy incident on a horizontal flat plate collector at any given latitude on the surface of the Earth. We also know how to evaluate the daily energy incident on a tilted flat plate collector located at any given latitude on any place on the surface of the Earth. We have seen a lot of equations. We shall try to consolidate all these equations and put them in a form in sequence so that it will help you later on in design and sizing of the PV panels. We shall use Octave for scripting and try to run the simulation and see the plot outs of the kilowatt hour per meter square per day versus the day number so that you know how this available energy function is over the year. I have here a text file, blank text file. I'm naming it as irrad.m, irrad short for irradiation.m. It's an M file. It's a script file which can be executed either in Octave or MATLAB. And then I'm storing that file, saved that file in PVSim. It is a scratchpad folder. So now let us start to populate this file, write the scripts. First, let us have the header comments. So these are all comment files, as you can see here. This description is that this file calculates the incident energy on a horizontal tilted surface given the latitude and the day number, where n is the day number, and I am considering only the non-leap years. And I am using Q for the latitude instead of phi because I can't type in phi in the ASCII in the text file. It will be in degrees, and we will later convert it into radians. So the first commands would be clearing the screen and then clear all the variables, and then now let us take inputs. So to take inputs, first we allow to mention the locality. So the locality, this again is a comment file. The latitude is 12 degree 58 minutes north of the equator, and this is the latitude of Bangalore. That is Indian Institute of Science, Bangalore has this latitude. So I just have taken that. You can as well choose any other latitude or locality of your choice. So Q is equal to 12.97. 58 minutes is in decimals 0.97, and this is expressed in degrees. We need to convert it into radians because it is always better to convert all degree units into radian units, the SI units, and the system of equations that will follow and the result that will follow will be consistent. Next, I have converted Q into radians. Q is equal to Q into pi by 80. Pi by 80 is the conversion factor from degrees to radians. So next, let me list out the constants. There is only one constant for us right now, that is LSC. LSC is the mean solar constant, which is 1.37 kilowatt per meter square, and that is what I have written. And now let us begin the calculation of the insolation and energy on all days of the year. So we have to take one by one. So let us say we take day number 1, n is equal to 1, and calculate H naught. Then day number 2, calculate H naught. So on for all the 365 days, we will calculate the H naught and put them in an array. So let us have a for loop, and this for loop will do this job of calculating. So if you see for n is equal to 1 to 365 and end for of this day number loop. Within the loop, what should come? So within the loop, let us see what we can have. First, let us calculate the declination. We know how to calculate the declination. So let us say a variable t is equal to 2 pi n minus 80 by 365, and then we use the declination relationship which we have studied. D delta was the declination, but I can't use delta, so I will use d for declination. 23.45 sine of t, or sine of 2 pi n minus 80 by 365, and this value is in degrees, and therefore I want to convert it into radians, and I am using this factor pi by 180. The declination is now expressed in radians. Next, I will calculate the extraterrestrial insolation scale factor, KLSC. We have LSC, we need KLSC, and that is calculated using 1 plus 0.033 cos 2 pi n by 365. I know n because n is an input, that is, it is a for loop input, and we can calculate k. Then after that I will calculate the hour angle. See, hour angle is a cos, that's cos inverse minus tan phi tan delta. So tan q tan delta, and you will get the hour angle. This is followed by calculation of h naught. H naught for the day number n. So if it is 1, it will be h naught of 1, h naught of 2, so on to h naught of 365. This will be an array. We use the equation well known, 24 k LSC by pi into cos phi cos delta sine omega SR plus omega SR sine phi sine delta. Now this will give you the h naught in kilowatt hour per meter square per day. We will also put into the days variable another array, the day number, so that we can plot h naught as a function of the day number. Then next we need to show the results, and let us plot. So what do we plot? We will plot days versus h naught, days on the x-axis, h naught on the y-axis, and then we shall have the grid, label the x label, y label, and the title. So this will complete our simple script file which will do the calculation of the energy incident, daily energy incident on a horizontal flat plate collector, and we should be able to see the results of this value computed for every day of the year. So we shall now save this file, and that's it, and we have the script file ready to function. We will open now Octave. I will click on the Octave. Octave will open. Now Octave has opened onto the screen. I will clear up this workspace and move into the folder of interest. So PVSim, this is where I have kept the files, and I will call errad. Now it will execute the script file that we just wrote, and we will get this. So you see that this is the h naught, kilowatt hour per meter square per day, computed for every day of the year, where the x-axis the day number. So day number is 1, 2, 3, and somewhere here is 80. We had calculated for 80. Remember that it is 10.54, and this is that one single calculation, and so on at 100, 200, 300, 365. These are the values that you calculate for the h naught. This is for a horizontal flat plate collector. This is how it will look like. Observe that this energy swings from around 8.25 to a max of around 10.7 or so. So this is a pretty large swing. So you see that during January, during November, December, the available energy on the horizontal flat plate collector is low. And during the mid year, during March, June, the summer solstice month, you see that the energy that is available is high. However, you should note that this calculation and plot of the energy, available energy on the horizontal flat plate collector is for a latitude, and it is without atmospheric effects. We will shortly discuss also the atmospheric effects. I shall now incorporate some changes in the script file so that we will be able to handle tilted surfaces too, so that we will be able to evaluate the incident energy on a tilted surface. So first, let me incorporate this line. So what I have done is set B is equal to Q. What it means is that beta, the tilt angle, is set equal to phi, the latitude angle. I am using B to represent beta, the tilt angle, tilt with respect to the horizon plane of the locality. And right now, I have just set it to a fixed angle Q, which is the latitude angle. Next, I need to incorporate here couple of lines, two lines, to estimate the omega SRT, the sunrise hour angle for the tilted surface. So it is actually the minimum of the sunrise hour angle of the horizon and the sunrise hour angle of the tilted horizon. So let us incorporate these two lines. So this line here is the sunrise hour angle of the tilted horizon, omega SR beta, which is equal to cos inverse of minus tan phi minus beta into tan delta. And this other line here is omega SRT, the omega SR of the tilted surface, which is minimum of omega SR and omega SR beta. So that is what we will use to evaluate HOT. Now next we will try to incorporate HOT. We have H naught. We will also obtain HOT, and that equation is like this: HOT is equal to 24 K LSE by pi cos phi minus beta, written as Q minus B, cos delta sine omega SRT. This is the sunrise hour angle of the tilted surface, omega SRT sine phi minus beta, written as Q minus B, to sine delta. Now this would give us the estimate evaluation of the energy incident on a tilted surface, tilted with an angle beta. Then coming to the display results, we have days versus H naught. We will also need days versus HOT, and then we will change the title slightly as H naught and HOT. So this would be our new edited file, script file. We will save it, and then this would be the saved file here. Now next we go to Octave. We will open Octave. I will clear up the Octave workspace screen and then go to the pvsim folder, and that is where the irrad.m is located. We will now run the script file irrad. Now that will result in this graph. So I will open it up, zoom it. So this gives us two graphs, the blue line and the green line. So the blue curve you have already seen is representing H naught in kilowatt hours per meter square per day. The green line is representing HOT, the energy incident on a tilted surface. Observe that the green curve HOT is better than the blue curve, because HOT is giving you over the entire year 1 to 365, day number 1 to 365, over the entire year, a much more uniform incident energy on the flat plate collector, which is tilted, compared to the blue line H naught, where the flat plate collector is placed horizontal. So the max energy minus the min energy here, the ripple, that will be the delta H ripple, is large in the case of the horizontal flat plate collector compared to the max energy minus the min energy of the tilted surface. Therefore, it becomes essential that we need to tilt the surface appropriately at a proper angle, such that you get the best collection of energy from the sun. We will see shortly what would be the best angle beta of tilt that we should provide for a given latitude. Let me further modify this script file so that we include a continuous variation in the tilt angle, so that we try to find out which would be the optimal tilt. So now here what I will introduce is a line. I have introduced B max or beta max. The tilt angle max has 30 degrees, 30 into pi by 180 radians. This is just a limit here for this example. You can set any limit, which means that I would like to make the variation in the tilt angle from 0 degrees to 30 degrees in steps, and see how the H naught T varies with respect to H naught. So we will introduce one more for loop, outer for loop, for B beta tilt angle, which is 0 to beta max, that is 30 degrees in this case. It could be any other value also, and I have done that in steps of beta max by 30, which is 1 degree in this case. So for every 1 degree, 0, 1 degree up to 30 degrees. And let us have the ending of the for loop here. So end of the for loop, end for the tilt angle. And what do we do in between? For every value of beta, every value of the tilt angle, you will see all this calculated as before. H naught will be calculated, HOT will be calculated, and it will be plotted. And then the next value of tilt angle, H naught and HOT, will be calculated and plotted. And you will see that H naught is same, doesn't vary, and HOT will vary with the tilt angle, and we will be able to see how this HOT moves and what would probably be the minimum value. Now what I am introducing here is, on the workspace screen we would like to see these parameters. HOT, minimum value of the HOT, important parameter to see. What is the H ripple? The maximum value of HOT minus the minimum value of HOT. What is that ripple? And we want to minimize that ripple so that it is as much as possible uniform throughout the year. Let us type in the latitude value also, and let us display the tilt angle, what is changing, and that is changing in steps of 1 degree. So you will see I am putting it in degree, converting and putting it in degree. So this would be the title line of the display. I would like to also put within the loop, for every beta calculation, display num to string of the minimum HOT, the max HOT minus min HOT, that is the H ripple, the latitude angle, and the beta angle. Okay, so this we can save, and before we save, let us pause for every tilt angle loop change. So I will put a pause here so that you will be able to stop the script execution and observe the waveform. So this we can save, and that would be the saved file. Let us now call upon Octave, open it and execute within Octave. So I will clear up the workspace screen. Let us go into our folder here and let us execute irrad. And then you will see you get something like this. I will now keep it side by side with the Octave screen. You keep observing here. You see that there is a display which is appearing, HOT minimum, which is this value, the minimum value here, the H ripple, the max H minus the min H, that ripple, the latitude angle is 12.97 degrees, and the tilt angle is 0. It is starting with the first value of the for loop, this is 0. And then next value, observe that this will keep putting up this values here in table, and this also will change. So you will see something like this, and keep observing these two. You see that as the tilt angle is increasing, the ripple reduces to a minimum and then increases. You see that ripple starts increasing beyond a particular value, and you can see the values here. In this fashion, the tilt angle is changing from 0 to 30 like what we had set. So the tilt angle is changing from 0 to 30 in steps of 1 degrees. Now what you could see is the H ripple and the minimum H naught, and you can probably see somewhere here at around 10 degree tilt. At the 10 degree tilt value for this latitude, at 10 degree tilt value, you find that the ripple is minimum 0.99, and the value is close to the minimum. The value of the minimum HOT is 9.52, which is the maximum minimum value. So which is advantageous for us, so that you can gain more out of this particular tilt angle from the solar PV panel. So this would become the optimum value to place the panel at this particular latitude at a tilt angle of 10 degrees. Now here again we have not yet considered the atmospheric conditions. We will consider that and get back again. But the concept is like this. You look for the difference between the max value of HOT and the min value of HOT. That is one parameter which is important. And also look at what is the HOT min, and the HOT minimum must be as high as possible. So this at 10 degree tilt angle, this is the most optimal and acceptable for us. In this way, you can find the optimum tilt angle. We have seen the result for a fixed tilt angle throughout the year. But if you change the tilt angle every day such that it faces the sun optimally, that is, you link it up with the declination delta, then you will get a much better incident energy on the tilted surface. So what I have done first is that save that previous file as irrad.b.m, which means that it's a fixed beta m file. I will put it up in the resource so that you can study that and then use it. And I will make one more modification in the irrad file here, which means I will remove the for loop for the tilt, and I have included here one line. Beta, or the tilt angle, is equal to phi minus delta, q minus d here. When the delta is equal to the latitude, which means the insolation line is such that it is passing through the latitude, of the location, then phi minus delta will be 0 at that place. At that time, the tilt can be 0, that is, it can be horizontal because the sun will be directly overhead. And at any other declination, let the panel track the sun. So making this modification and keeping all the equations same, let us see what you will get when you run the script in Octave. So I have saved that, and then let us run irrad. And when I zoom it up, so you see two curves, the blue curve representing H naught and the green curve representing HOT, the energy incident on the tilted surface. However, here the tilt angle is changing every day. On day number 1 you have one tilt angle, day number 2 another tilt angle, so on. Day number 365 another tilt angle. So it is tracking the sun throughout, and you observe the improvement in the energy curve, and you see that it is really much higher than H naught and the previous fixed tilt angle values, and you see that the minimum HOT itself is much higher than 10 kilowatt hour per meter square per day. So this is the benefit you would get by tracking it on a daily basis, but it is cumbersome to track because you need to fit up motors and the mechanical arrangements where you have to pay for that. So in order to keep it simple, people generally have a fixed angle tilt and try to optimize on the fixed angle tilt which you would place. The other option is to have seasonal tilt. So every season, let us say 3 times or 2 times in a year, you can change the tilt angle and keep it and maximize the energy that you collect over the year.